Some of the most important results from electrochemistry are the relationships among the electropotential, Gibbs free energy, and the equilibrium constant. Measurement of the cell EMFs gives you yet another way of calculating equilibrium constants. We showed you before some relationships between equilibrium constants and other values. This relationship between electropotential and K is as follows. E of your cell, meaning your standard cell, since it has that superscript 0, meaning that 25 degrees C, is equal to 2.303 time R time T divided by NF time the log of K. The 2.303 comes from the fact of going from natural log to log conversion factor. R is your ideal gas constant. T is your temperature in Kelvin. And since we're talking about superscript E, we're talking about standard potential. We're talking about 25 degrees C. F is your Faraday's constant. N is your number of electrons. That's the number of electrons you transferred. The last example in the previous homework lecture, remember that was 6 electrons between the iron and the aluminum. Okay, so N would be 6 in that case. Time the log of K, where K is your equilibrium constant. That is your relationship of your products over your reactance rates to their coefficient. Notice 2.303 R and F are all constants, and if we're going to talk about having this reaction of a standard cell, meaning at 25 degrees C or 298 Kelvin, then that's a constant as well. So we can take all those values, the 2.303, the R, the T, and the F, and make a new constant, which is equivalent to 0.0592. So that 0.0592 is a combination of those constants. The R, the temperature at 25 degrees C, which is 298 Kelvin, Faraday's constant, and the 2.303. Now realize that this equation is that of a standard cell, therefore we are at 25 degrees C for this equation, which is equal to 0.0592 divided by N, which is your number of electrons being transferred in your balance equation, times the log of K, where K is your equilibrium constant, which is set up with your products over your reactants, each one of those raised to their coefficients. Say that we did several chapters, throughout several chapters in this course. Remembering that solids are 1 and pure liquids are 1. Alright, let's do a calculation with this equation. Previously we determined the standard EMF for the following cell, for your zinc copper cell, is 1.1 volts. Remember, we did this calculation already. Okay. We already did this calculation where we had the zinc 2 plus at 1 molarity, copper 2 plus, 1 molarity copper. This is a standard cell. We basically saw that since zinc is on the left side, that it's being oxidized and copper is being reduced. So we took our potential, zinc, and we had to flip the reaction from its electropotential. And we have our copper, we would use it just as it is on the potential table. So that gives me E of 0.76, changed the sign since I flipped it, E of 0.34 volts for our potential of our copper. We need to make sure we had the same number of electrons balanced, which in this case they're both 2. Zinc is given up 2 and copper is taken on 2. Add this up, we get an overall balance equation is zinc plus 2 coppers, copper plus copper 2 plus, gives me zinc 2 plus plus copper. And the E of the cell is a case of this adding up to E's, which is 1.10 volts. So the important thing to use the equation in the problem that we're about to do is the following. Okay, we got to realize that it's 2 electrons is our N. Okay, so our N is equal to 2 because the 2 electrons in our balance equation. Okay, and the electron potential is 1.10 volts. So continue on with our problem. We know the reaction, we know the E of that potential of that reaction is 1.1 volts. When they'll plug this into our equation, E of the cell, standard cell, is equal to 0.0592 divided by N times the log of K. We know that N is 2. So now we can rearrange this equation. We multiply by 2 on both sides and divide by 0.0592 on both sides. which gets us the log of K is equal to 1.1 times 2 divided by 0.0592 equal to 37.2. Now we have to get rid of the log, so we do the anti-log of both sides. So when we do the anti-log, that basically means we're going to do 10 to that function, 10 to that value. So 10 to the 37.2, that's your 10 to the x on your calculator button. Remember, if we're doing the natural log, anti-log, it would be e to the x, okay, but we're doing the base 10 log, LOG, which is 10 to the 37.2, which gives me 1.6 times 10 to the 37th. Going by correct sig figs, since we got one digit past the decimal, we have one significant figure, which means Kc is equal to 2 times 10 to the 37th. Notice this is a very large number, and therefore the equilibrium lies to the right, which means it's a spontaneous reaction, which agrees with the E value, which is a positive value. It also says it is a spontaneous reaction. Now, recall that everything we have done so far has been with a standard cell. If an electrode is a measure of the extent to which concentration in a half cell differs from an equilibrium value, then concentration will affect that equilibrium and vary that potential. Electrode potential is dependent on the concentration. The further we are from equilibrium, the greater the potential, the higher that voltage. Remember that potential in the tables is for standard conditions. 1 molarity, okay, 1 molarity, 1 atmosphere, 25 degrees C. If the concentrations are not standard concentrations, then that cell potential must be corrected. Basically, the potential for your non-standard cell will be equal to that standard cell potential with a correcting factor for non-standard conditions. So we have to still calculate the standard potential, but then we have to do this correcting factor to figure out the non-standard. Equation looks like this. You have your E of your cell. Okay, this is your non-standard cell. Okay, is equal to your E naught, which is basically your standard cell. Okay, potential minus 2.303 RT NF times the log of Q. Now we're going to say Q because it may or may not be at equilibrium, so it'll be whatever your initial values are. Once again, we can take that 2.303 RTF and say, let's talk about it at 25 degrees C. That's everything that we're going to do. And we can make a new constant. Okay, that 2.303 RTF can basically go back to that constant we talked about before. And we can rewrite the equation E of the cell, meaning your non-standard cell potential, is equal to E naught, which is your standard cell potential, minus 0.0592, which is that 2.303 RTF, divided by N, which is your number of electrons that's transferred, times the log of Q. Q being your products raised to their coefficients divided by the reactants in their coefficients, raised to their coefficients. This is what we refer to as the Nernst equation. Okay, this is what we're doing, and we're going to do everything at 25 degrees C in this class. So this is the equation you use if it's a non-standard cell. You figure out your potential for your standard cell and then use the Nernst equation to calculate the E of the non-standard. Now, basically that second half of the equation, okay, the second half of the equation is basically a correcting factor. So the E of the non-standard cell equals the E of the standard cell with this correcting factor attached. Notice that if they'll talk about the concentrations of everything being 1 molarity, well, the log of 1 divided by 1 is 1. The log of 1 is 0. Okay, so that whole correcting factor turns into 0. So if the concentrations of all your species are 1 molarity, then you're taking the log of 1, which is 0, and the correcting factor is 0. So your standard cell equals the non-standard cell concentration. Potential. Therefore, you could use the equation all the time if you wanted, but that's just more work than needed. If it's a standard cell, you know you stop as soon as you figure that potential. Non-standard, we have to go on and use this equation. Let's look at an example. What is the EMF, the E of the cell, for the following cell at 25 degrees C? I have zinc and zinc 2 plus at a 1.0 times 10 to the minus 5th molarity. I have copper 2 plus at 0.1 molarity. Okay, what I'm trying to do is find the potential of this cell. Well, this is not a standard cell because I don't have 1 molarity in zinc and 1 molarity in copper. So therefore, I'm going to have to calculate my potential for the standard cell, then use Nernst's equation to calculate the E of the entire cell for the non-standard cell. So I have my givens, which is both written as reductions coming from the table. We have our short notation. We know on a short notation that the species on the left side is my oxidation and the one on the right side is my reduction. So from this we can decide whether we have a spontaneous or non-spontaneous reaction based on what's being reduced. Copper is being reduced, and it's the larger potential. Therefore, in a spontaneous reaction, we would expect copper to be reduced. So we expect the potential of our standard cell to be a positive number. Okay, be a spontaneous voltaic cell. That's for the standard cell. We don't know what's going to happen with the non-standard cell because those concentrations can shift it for one way, in higher voltage or lower voltage, depending on the concentration changes. So what we're predicting here is, since the larger E is going to go in reduction in this setup, the way that this is set up in this short notation, then we expect this, at least the standard cell, to be a positive voltage in a spontaneous reaction. So we know that zinc's being oxidized, so we're going to flip that reaction and change the sign. Okay, so we flip the reaction, change the sign, and the copper is being reduced, so we use that equation just like it's written. We need to balance the electrons. They're both 2, so I don't have to multiply by any factor. So now I can just add the 2 equations up, which gets me zinc plus copper 2 plus, gives me zinc 2 plus copper. And the E of the cell is formed by just adding up the 2 E potentials, which is 1.1 volts. We've done this a couple of times already. However, this is not a standard cell. Okay, we have other than 1 molarity concentrations, so then we're going to have to use the Nernst equation to calculate the potential of that non-standard cell. So then we use our Nernst equation, which is E of the cell equal to E naught of the cell, meaning your standard potential, where your E of the cell is your non-standard. Okay, minus 0.0592 divided by N times the log of setting up your Q, which would be your products, which would be your concentration of your zinc plus to the first power, because it has a coefficient of 1. Okay, and then you have copper solid. Solids have an activity of 1, so it's not part of the expression, divided by your zinc solid, which has an activity of 1, divided by your copper 2 ion concentration, which also has a coefficient of 1, so it's to the first power. Both cases, it's to the first power. We can plug in those values. E of the cell is equal to 1.10 volts, which we calculated, minus 0.0592, divided by the number of electrons that transferred in the balance equation, which was 2. Now, many of the equations I'm going to do are going to be 2 electrons. It's not always 2. Okay, remember when we did the aluminum iron example in the previous homework lecture, it was 6 electrons, so N would be 6 in that case, but many of the examples we will do will have 2. So I don't want you to get the idea that it's always 2. Time the log of, plug in the concentration of zinc 2, which is 1 times 10 to the negative 5th, divided by my concentration of copper, which is 0.1. Now mathematically, I got to figure out my numeric number from that division, take the log of that number, time 0.0592, divided by 2. If I do all that, okay, then that numeric number, okay, this whole new numeric number, okay, is equivalent to a negative 0.12, okay, and that's volts. Okay, that's volts as well. So I got 1.10 minus 0.12, which means plus 0.12, which gets me up 1.22 volts. You can see the increase by 0.12 volts. It's still voltaic, it's still spontaneous, so it changed a little bit in the amount of voltage by changing the concentrations of those species from being 1 molarity. The change in concentration can vary that potential to go up or go down. All right, everything we've done so far has been voltaic or galvanic type cells. Let's talk about electrolytic. An electrolytic cell is an electrochemical cell in which an electric current drives an otherwise non-spontaneous reaction, meaning that reaction is not going to go the way it's written, but if I can put some voltage into the system, I can make it go. The process of producing a chemical change in an electrolytic cell is called electrolysis. Many important substances such as aluminum metal and chlorine gas are produced commercially by electrolysis. This is how we plate gold and silver onto jewelry. We basically set up the ring as the cathode and then plate out that metal onto it. Let's look at an example. I got a silver electrode and a copper electrode. And we know by the way this is written up, okay, that the silver is being oxidized and the copper is being reduced. Now here's my reduction potentials. Let's look at that and see if it's a spontaneous or non-spontaneous reaction the way it's written. In this particular one, I have silver being oxidized, and notice that silver has the largest potential. Okay, it has the largest potential, but it's being oxidized. We know in that case, the larger potential one wants to be reduced in the spontaneous reaction. Our larger one's being oxidized, so what we have is a non-spontaneous reaction, electrolytic cell. So we expect to get some potential voltage that's a negative value, okay, for the standard cell. But since this is a non-standard cell, that concentration may shift it one way or the other. So we have to do calculation to figure it out. We can predict the standard one, we cannot predict the non-standard one. So you have your reaction. We have silver being oxidized. So I have to flip the reaction and change the sign. So now I have my negative on my 0.8. I have my copper being reduced, and I write that potential of 0.34. Now I need electrons to balance. So I need silver's giving up 1 and copper's taking on 2. So I got to multiply the whole silver process by 2. And notice I'm going to multiply the silver solid, the silver ion, and the 2 electrons by 2, but I will not multiply the 0.8 by 2 because it's an intensive property. I add them up. What happens is my 2 electrons cancel, so I end up with 2 silver solids plus copper 2 ions gives me 2 silver ions, silver 1 ions plus copper solid, and the E of that cell adding up that negative 0.8 and that positive 0.34 gives me a negative 0.46 volts, which is what we expected. We expected an electrolytic non-spontaneous reaction by the way this short notation is set up. However, that's for a standard cell. That's 1 molarity of silver and copper, but we do not have that. We don't have a standard cell, so we're going to have to correct for that. How do we correct for it? Well, we use Nernst's equation. So we know the potential for our standard cell, so we set up our Nernst equation, which is the E of your cell, which is your non-standard potential, equal to your E naught, which is your standard potential, minus 0.0592 divided by N times the log of setting up your reaction, be your products, which is your concentration of your silver ion to the square, because of that 2 coefficient. Then I have copper solid, which is 1, divided by my silver solid, which is 1, and I have copper 2 ions to the first power. Now plug in my values. We know that the potential of my standard cell is a negative 0.46. I got 0.0592 divided by the number of electrons in my balance equation, which is 2. Log of my concentration of silver, which was given to me at 1 times 10 to the minus second. That value squared divided by 1.5. So mathematically, I will do my division first. Then take the log of that number, multiply by 0.0592 divided by 2. That whole value, when it's finished being calculated, is a value of a negative 0.124 volts. Okay, plug that in. That's negative 0.46 minus a minus, which is a plus, which gives me a negative 0.34 volts. So it's still electrolytic, but it's less voltage. Less voltage needed for that reaction. Okay. Let's look at a little bit harder problem. So this one has a lot more in it. Okay, we have a platinum electrode and we have our uranium 4 plus going to uranium 6 plus. You've got UO2, which is a 2 plus overall charge. That means in there that uranium has a plus 6 charge. So we're going from a plus 4 to a plus 6, which is an oxidation process. But you know what should be happening on that left side is oxidation. On the right side we have reduction. We have iron 3 going to iron 2. Now we can make a prediction on the potential of our standard cell. Since the iron is being the case that it's being reduced because it's on the right side, and it has the larger E, okay, potential, meaning the more positive, or if I'm comparing two negative ones, the one negative number that's closer to 0, okay, it's being reduced, then it's a spontaneous reaction. So we expect some positive potential when we do a standard. Now, the nice thing about the electrochemical cells is that you don't have to balance the redox like we did at the beginning of the semester. I give you the half cell, so it has everything there. All you got to do is flip it and calculate with the correct number of electrons. So if we know that uranium is being oxidized on the left side, then we got to take that reaction and flip the reaction and change the sign. In the iron reaction, we would use just like it's written. So I have my iron 3 going to iron 2 at 0.771 volts. And I have my uranium reaction, which we flipped it now. And I have to change the sign, okay, of my potential because I flipped the reaction. Now I need the electrons to be balanced. So I got my iron is taking on 1 electron, and I'm giving up 2 on the uranium, so I need to multiply that by 2. And I'm not going to multiply the potential by 2 because it's an intensive property. Then I can have my electrons cancel, bring everything down. That gives me 2 iron 3s plus uranium 4 plus 2 waters, gives me UO2 2 plus 4 H pluses, and 2 iron 2s. The potential adding up that 0.771 minus that 0.334 gives me 0.437 volts, which is the potential for a standard cell. But do I have a standard cell? The answer is no. I have many different concentrations. There's not all 1 molarity or 1 atmosphere for gases. So we're going to have to use the Nernst equation, which is E of my each cell is equal to my E of the naught cell minus 0.0592 divided by N, log of my concentration of UO2 plus to the first power, my H plus to the 4th power, remember I got a 4 coefficient, iron 2 plus to the 2nd power. Okay, that's where these powers are coming from, divided by my iron 3 to the 2nd power, my uranium 4 plus to the 1st power, and water liquid is my activity of 1. So I need to plug in my values. My E naught in the cell, my standard cell potential is 0.437 volts minus 0.0592. Well, N is my number of electrons, which in the balance equation was 2, so that's 2 again. Log of the concentration of my UO2 plus was 0.150. Concentration of the H plus is 0.03, that's to the 4th power. My iron 2 is 0.01 to the 2nd power. My iron 3 is 0.025 to the 2nd power. And my uranium 4 is 0.2. Mathematically, if I take all this, doing my concentrations, multiplying first, taking the log of that value, multiply it by 0.0592 and divide by 2, that value is a negative 0.237 volts. Okay. Plug that into my equation. Well, I got a negative and a negative. That turns into a positive, which means I get 0.437 plus 0.237. Added up, I get 0.674 volts, which is a positive voltage, and it's still a voltaic cell, a spontaneous reaction. Now, what if I have changed this problem, and instead of saying H plus, I said, instead of having H plus, I said I have HCl. Would that change anything in this problem? Instead of saying H plus is 0.03 molarity, what if I told you HCl was the acid I was using and it had a 0.03 molarity? Would that change anything? Well, what is HCl? That's a strong acid. What happens to a strong acid? Ionizes at 100%. Therefore, my hydronium ion is still 0.03. So the answer to the question is, it's a strong acid, so the problem would be exactly the same. It wouldn't change a thing. Now, what if I worked this same problem, but instead of saying I had HCl or H+, I tell you that I have HCN as my source of my hydronium ion. Would that change anything? Yes, that's a weak acid. We know that weak acid ionizes less than 5%, so that H plus is going to be less than that 0.03, 5% of that 0.03. So we need to calculate that. So that goes back to what we learned with weak acids. So we have to handle that. So let's do that first. So we take that. And we write our hydrolysis, our HCM, giving us hydronium and CM minus. Then do our ice table. We have our 0.03 concentration of HCN to start with. We have our approximate 0, meaning we're neglecting the water, and CM minus. We know it's going to the right, so we have our minus chains on the reactant side, pluses on the product side. And I have X as my relationship. Everything's 1 to 1, which means at equilibrium I got 0.03 minus X, X for hydronium, and X for CM minus. Next question is, how are these related? Remember, those are related through Ka. So then I'll set up my Ka expression. It's equal to my hydronium ion concentration times my CN minus concentration divided by my HCN. Plug in the values, X, 0.3 minus X, which gives me X squared divided by 0.03 minus X. Now, I can use a quadratic formula, or there's a way we got around this. We said that we looked at the powers of 10. 0.03, that's the same thing as 10 to the minus second. My Ka is 10 to the minus 10th. That's 8 tenths difference. We said if it's 3 or more difference, then we can neglect X. So we go ahead and get rid of that X, which then means I have X squared is equal to 6.2 times 10 to the minus 10th times 0.03 after I multiply both sides by 0.03. Now how do I get rid of the square term? Square root of both sides. Okay, which then means I have X is equal to 4.3 times 10 to the negative 6 molarity. Then I got to ask myself, what does X represent? Well, it represents the hydronium ion concentration. It also represents my concentration of my CM minus, which I'm not worried about in this problem. Okay, but it does give me my hydronium, which tells me my H plus concentration that I have to plug into my Nernst equation. So I can go from here to my Nernst. I know that E is equal to my 0.437 minus 0.0592, which is divided by 2 because there's 2 electrons transferred. Log of my 0.015 and my 0.01 squared for my concentrations. My 0.025 squared and my 0.2, all those stay the same. Okay, nothing changed in that. The only thing that's changing is that hydronium ion concentration, that H plus ion concentration. Before it was 0.03 to the 4th power, but since this is a weak acid now, okay, that weak acid now changed that H plus concentration, and we had to calculate it, which is now 4.3 times 10 to the minus 6. Now that is going to go to the 4th power. Do the calculation, okay, this whole numeric number, when I calculate it, ends up being a negative 0.692 volts. Once again, I have a negative times a negative, which makes that a positive. So it's 0.437 plus 0.692, which gives me a total of a 1.129 volts. It's still a spontaneous reaction of voltaic cell. However, the voltage has doubled. By putting in a weak acid over a strong acid, you can see that the voltage has doubled. So which acid I use is important to figure out how much voltage is going to be generated in this process. Let's look at this one. Okay, we know that silver is being oxidized because it's on the left side, and I know that hydrogen is being reduced because it's on the right side. Silver has the larger potential, 0.799, but it's undergoing oxidation. So again, we're going to expect an electrolytic cell here. We expect some negative voltage because the higher potential is undergoing oxidation, not reduction. So we'll go ahead and take the silver and flip that equation and use our hydrogen as it's written, which then means I got to change the silver potential to a negative 0.799. I also need to balance the electrons, so in this case I got to multiply by 2. Okay, as I cautioned you before, everything I'm doing is 2 electrons, but not everything is 2 electrons, just the ones that we've been handling. Add up the reactions, I get 2 silvers plus 2 H pluses, gives me 2 silver ones plus H2. Add up my potentials, and I get a potential for this reaction to be a negative 0.799 volts, and that's what we predicted. Okay, so for your standard cell, okay, this is your potential for your standard cell as a negative 0.799 volts for this reaction. Do I have a standard cell? The answer is no. Okay, I don't have 1 molarity for everything or 1 atmosphere for gases. So we got to use the Nernst equation. So we'll go on from there. It's going to equal to E of your cell minus 0.0592 divided by N times the log of your concentration of your silver ion squared times your partial pressure of hydrogen divided by your concentration of your H plus squared. And then you have your 2 silvers, which is a solid, so that's a 1 activity. So that's not part of the expression. Now where do I get these values from? Well, the H plus concentration, we have that, and we have the partial pressure of your hydrogen in the problem on the reduction side. Now for the H plus, it's in the form of HBr. What is HBr? That's a strong acid. What happens to strong acid? Breaks up 100%. So that tells me my H plus concentration. So it's 0.02. So we know that one directly. What about the H partial pressure of my hydrogen? Well, it's 0.8 atmosphere. It's given to me. It's giving me my partial pressure directly. So I have those values directly. What about my silver ion concentration? Is that given to me directly? The answer is no. We don't know what that value is. We're going to have to calculate it. You can see it tells me I got a saturated solution of silver chloride, and I have some sodium chloride in there as well. So what we have here is a KSP problem that also has a common ion. So what we have to do is work out a common ion problem for our insoluble salt to figure out the amount of silver concentration that's available for this reaction. So what we start off as we've done in the past, we take the soluble salt first. Okay, so I'll take my soluble salt first, write that up. Since it's soluble, I know the concentration of the sodium and chlorine is going to be the 1-to-1. I know that this concentration of that chlorine is going to have to be taken accounted for in my table when I do my insoluble salt, which is next. Right, my insoluble salt, that silver chloride forms silver and chlorine ions. I'm trying to figure out the solubility of that silver chloride. Okay, and I know the relationship between silver chloride and silver is a 1-to-1 and 1-to-1 for the chlorine. So setting up my table, we know that I have this initial amount of chloride ion, which is 0.02. Okay, remember that's coming from my soluble one. And I know the relationship between silver chloride and solubility of silver chloride and silver is S, and the relationship between my solubility of silver chloride and chloride is S, which means at equilibrium I have S amount of silver and I have 0.02 plus S amount of chloride ions. How are these related? They're related through KSP. I'll set up my KSP. KSP is equal to 1.82 times 10 to the negative 10th, equal to my concentration of silver ion times the concentration of a chloride. So then plug in those values, S and 0.02 plus S. Now once again, I can do some arithmetic or get around it. Well, I want to compare that 0.02, which is 10 to the minus second. Compare that to the 10 to the minus 10th on my KSP. That's a factor of 8 difference. We said if it's 3 or more, we can get rid of that S. So we think S is much smaller than that 0.02. Okay, much smaller than that 0.02 value. Therefore, we will get rid of the S. And to now continue on my math will now mean I got 1.82 times 10 to the minus 10th divided by 0.02, which is 9.10 times 10 to the negative 9th, which tells me my molarity of my silver chloride, my molar solubility, okay, of my silver chloride, as well as my concentration of my silver ion, which is what I want in this particular case. So now I have that value that I can plug into my potential equation, my Nernst equation, which gets me E of the potential of my non-standard cell equal to the E of my standard cell minus 0.0592 divided by N log of my concentration of silver squared, which is that concentration we just calculated, okay, which is the concentration we just calculated, which is going to be plugged in here. Partial pressure of your hydrogen, which we know, and the concentration of my hydrogen ion squared. Plug in the values. I got a negative 0.799 minus 0.0592 divided by the number of electrons transferred, which was 2. Log of my 9.10 times 10 to the negative 9 squared, times my 0.8 divided by my 0.02 squared. Okay, then mathematically, doing the math on this, okay, that whole correcting factor is going to be a negative 0.378 volts. Once again, a negative and a negative will give me a positive, which gets me a negative 0.799 plus 0.378, which gets me a negative 0.421 volts. Okay, because you can see how having a saturated solution there is going to change the voltage and go down by a good bit. Still electrolytic cell with a negative voltage in a non-spontaneous reaction. The last three examples I gave you here are more complex electrochemical cells. I don't plan on giving you any complex ones on the test. It was just a good idea to show you some things that kind of show you how things are interrelated between the things we learned previously in this stuff. It gives you a good start since the final exams coming up. It gives you an idea of refreshing your memory on Kas and strong acid and KSP stuff. So I just threw these in there. What you're responsible for is a straight standard cell or a non-standard cell where you plug it into the Nernst equation directly and not having to do any extra calculations for concentrations, etc. All right, the last topic we're going to cover in electrochem is the stoichiometry of electrolysis. What is new in this type of stoichiometry problem is the measurement of the number of electrons. Okay, we do not weigh electrons directly. Okay, we don't have a mass of electrons, so we need to figure out a way to figure out how much electrons is involved in the transferred in any process. So rather, what we do is we measure the quantity of electric charge that has passed through the circuit and relate that to the mass of the electrons, the moles of electrons. To determine this, we must know the current and the length of time that has been flowing. Okay, so if we know the current and the length of time, then we can figure out how many moles of electrons has went by, and we can relate that moles of electrons to the mass of something that we're trying to calculate. Basically doing stoichiometry problems. Electric current is measured in amperage. Okay, and amperage is a capital A. It is the base SI unit for current. It's equivalent to 1 coulomb per second. So a conversion factor you need to be familiar with is 1 amp is equal to 1 coulomb per second. Okay, 1 amp is equal to 1 coulomb per second. The quantity of electric charge passing through a circuit in a given amount of time is given by the following equation. Your electric charge, meaning your coulombs, is equal to your electric current in amperage, or coulombs per second, is equivalent, time your time lapse, which is in seconds. Has to be in seconds because we need the seconds to cancel out. Okay, so if we know the electric current and I know the time lapse, I can figure out how much coulombs has been associated with that process. From there, we can go from coulombs to moles of electrons, and from there to the mass of the substance we're trying to calculate. Couple of notes. Okay, remember that 1 amperage is equal to a coulomb per second. That's important when you're trying to cancel units. Let's look at an example. When an aqueous solution of potassium iodide is electrolyzed using platinum electrodes, the half reactions are as follows. I got 2 I minuses, gives me I2 solid plus 2 electrons. I have 2 waters plus 2 electrons, gives me hydrogen gas and 2 OH minuses. Okay, actual question is, how many grams of iodine are produced when a current of 8.52 milliamps flows through the cell for 10 minutes? So if I have this much current and I have this period of time, 10 minutes, we want to know what is the mass of I2 formed. Okay, for just 10 minutes at 8.52 milliamps. So the first thing we got to do is convert that current and that time into coulombs. Okay, now remember when we plug it into the equation that we have to plug it in at certain units. We know that the equation is electric current charge, coulombs, is equal to electric current in amps, which is coulombs per second, time your time lapse in seconds. So I want to plug this current in, but I want to plug it in as amperage. That's in milliamps, so we know there's a conversion factor. There's 1,000 milliamps for every 1 amp. So dividing by my 1,000, I can figure out my milliamps, okay, convert them into amps, okay, which basically means it'd be 8.52 times 10 to the minus third amps, okay, or coulombs per second. And then I got to change 10 minutes to seconds. There's 60 seconds per minute, which basically means there's 600 seconds here. Plugging that into my equation, my charge then will equal to 8.52 times 10 to the negative third coulombs per second. Remember that an amperage is a coulomb per second. Times 600 seconds, which I wrote in scientific notation, which is 6.00 times 10 to the second seconds. Okay, so what happens then is my seconds cancel, and I end up with 5.11 coulombs. What we're going to do now is somehow figure out how we're going to get from coulombs to the mass of I2. Well, there's a conversion factor that I told you to remember back several homework sets ago. I wanted you to remember that there's 96,500 coulombs for every charge of 1 mole of electrons. Okay, so every one charge of every mole of electrons. This conversion factors can allow us to go from coulombs to moles of electrons. And once I'm in moles of electrons, there's a relationship, okay, between my substance and the number of moles of electrons being generated. So, looking at our reaction, I'm starting off at 5.11 of coulombs. So first step, I want to change from coulombs to moles of electrons. So I'll plug that in, and we can see my coulombs cancel. This is 96,500 coulombs. Okay, so my coulombs cancel. So now I'm in moles of electrons. Now I gotta get from moles of electrons to my substance. Well, there's a relationship, okay, between my moles of electrons and my substance, which is what type of relationship? There's a 2 to 1. Okay, for every 2 moles of electrons, which is coming from right here, there's 1 mole of my I2. So that's where that relationship's coming from. There's 2 moles of electrons for every 1 mole of I2 coming from that balanced half reaction. So then my moles of electrons cancel. So now I know how many moles of I2 is associated with that amount of coulombs. Okay, that 5.11 coulombs. But I want mass. How do we go from mass, from moles to mass? Well, that's through molar mass. It goes back to a Gen Chem 1 process. So molar mass, there's 254 grams of I2 for every 1 mole of I2. And I put it this way because I want the moles of I2 to cancels. So if I multiply all this out, I figure out that there's 6.73 times 10 to the negative third grams of I2. So this is the amount of I2 that's going to be generated from that amount of coulombs, which came from that 8.52 milliamps for 10 minutes. Okay, it's going to generate that amount of coulombs, which then will produce this amount of I2. Homework 50 gives you questions about non-standard cells and also this stoichiometry of electrolysis.